Hello friends, welcome back. This is week 6. Till now, in first 5 weeks, we have the basic information about the 3D printing. We understood about the protocol for the polymer, metal, gel 3D printing, and we have seen the various applications. Now, in this week, we will be mainly focusing on the fabrication of the sensor. We will see how we can make the biosensor for different application, and then we will see the use of these biosensor in the form of different case studies. So, starting with the basic introduction of the sensor. Sensor, we as we all know, something we are interested to sense. So, this can be a device or a component or a system, or it can be a module which can be used for monitoring the occurrence of surrounding and transferring the data to some electronic system. Nowadays, most commonly used is the computer processor. So sensor perform physical transformation of physical occurrence into the quantifiable digital signal, and what we are interested is it should be displayed and we should be able to interpret the data in a simple way. So if I see the basic working of the sensor, I have some physical quantities which may be in the form of some humidity value, some pressure value, some temperature value, force value. Actually, all these stimulus we are going to use for the 4D part, and for the 4D part, the sensing capability has to be introduced. That is why we need to understand some of the basics of the sensor, right? So these physical quantities being sensed, and the sensing of these physical phenomena, so converting them into the some electrical signals, maybe in the form of small voltage signal or current. Then these electrical signals like voltage, current, frequency, we are going to interpret to understand the various physical occurrences of the system. So that is the basic idea of developing these type of sensor. So what is the importance and the need? Because we are interested in the automation, we are interested in safety and efficiency. So all these things are required in healthcare, in transportation, in smart devices. So these sensors are designed for precision, for reliability and efficiency in the computing information. And of course, these sensors are one of the integral part of the IoT system for the robotics and AI driven systems. There are n number of sensors. Right now, for the 3D printing part, we are interested in a one typical type of sensor that is basically based upon the concept of the microstrip patch antenna. So before we understand the actual functioning, let me give simple overview how this work. See, I have a substrate which is a dielectric material, and on that substrate I am making one conducting part on the top and one conducting part on the bottom side, and then I am giving a AC signal to it and trying to generate a electromagnetic wave. So after some distance, the electromagnetic wave from the top portion and the bottom portion, they are superimposing, and the place where I am getting the first peak, I am calling it as a resonant frequency. So the whole story of working of this type of sensor is moving around the capturing of the first peak that we are calling at the resonance frequency peak, right? So if I am not knowing at the any moment of time what is the dielectric property or the dielectric constant of that material, we use a concept called ring resonator. So for a typical ring resonator, as you can see in this figure, I have a typical conducting ring which you can see over here, and then I have the feed lines. These are also the conducting part. In most common microstrip patch antenna, these are made by the copper plate, which is normally available in the form of a copper sticking tape that can be installed in the form of ring or in the form of these feed lines. Then it has a n number of application in optical communication, in microwave, in RF filters, in sensing, specifically chemical biological sensor. Then we have wavelength division, multiplexing system, spectroscopy. Then of course in multiplexer this is used in a big way. So there are some common terms like the width, the coupling gap. This is the basic substrate that I am interested, the mean radius, width part, and the feed length. So all these things are some of the basic requirement for developing a ring resonator. Then if I talk about the microstrip patch antenna, it looks something like this. So I have a substrate. I am interested in dielectric constant, which is represented by the epsilon r. Normally, for the commercial sensor, the value of this epsilon r varies between 2 to 14, right? So this microstrip patch antenna is again consisting of a conducting patch on one side of the dielectric substrate. So this is the dielectric substrate and this is the conducting patch, and on the other side this is a ground plane. Ground plane means the whole surface is having a conducting behavior, right? So application again in mobile and satellite communication, radio frequency, telemedicine, radar, biomedical, and the health monitoring applications. Now, for the development of sensor, what I need is I must understand what is the dielectric behavior of my substrate, right? So for that purpose, one of the basic instrument that is in front of you, we call it as a impedance analyzer. We use this system, of course, available in our lab, and this can give me some information about the dielectric behavior up to 8 megahertz. There are, high range of impedance analyzer available that can give me the output in the range of gigahertz, or sometimes for the terahertz. But for simple application, for the low cost or lab like solution, we normally have the input from kilohertz to the megahertz range. But along with this, we have the facility for seeing the effect of temperature on the dielectric constant, because this is required for the 4D application. You can see this in small video how this impedance analyzer is used for getting the required dielectric constant. So basically what I need is a small sample. Normally we make a disc type sample, let us say 10 dia, 1 to 2 thickness, and on both side of the disc I am basically attaching a silver coating, and then applying a voltage around this system, and seeing the effect in this range, the effect of temperature, and I am getting a plot for the dielectric behavior of that material, right? So once I have a data for the frequency in megahertz, then if I want to convert it into the gigahertz specifically for the microstrip patch antenna application, so one of the ways we can use a mathematical model like a Debye relaxation, which involves some series of the standard equations as shown in this slide. So this equation 1 and 2 we normally use, and here this epsilon dash is called the dielectric constant, and epsilon double dash is the loss factor. Epsilon s is the static permittivity. Epsilon infinity is the highest electric permittivity of the required material. So omega angular frequency and the relaxation time 1 to 10 to the power minus 9 second, that is kept constant, right? So based upon this data, what I came to know is what is the epsilon dash, that is the electric constant at 2.45 gigahertz. Whatever we plan to have a sensor, we use this data to feed it into the HFSS module of the ANSYS, that is high frequency structural simulator software, and basically we can calculate the dimension of the ring or the dimension of the microstrip patch antenna. Otherwise I can use some mathematical way also for the calculating the epsilon r using a ring resonator test. So for that purpose, again there are some set of equation which are of course very much available in the literature. So first I need to calculate the ring resonator r, that is the mean radius. Then using the equation 3, so basically we came about r. Here the lambda g that is showing in the equation 3 is the guided wavelength that is calculated by the equation 4, and where epsilon effective is the effective electric constant that actually we have calculated. C is the velocity. Then again there are set of equation like 5 to 10 you can see over here. So for based upon that equation we are able to calculate the exact dimension of the ring and the size of the feed lines, right? So based upon this we came about the some dimension of the ground plane, dimension of the patch, dimension of the electric material. Here is one example has been quoted. PLA material, the relative electric constant epsilon r was coming to 8 into 10 to the power 6 hertz, right? And once you need it for in gigahertz with a different epsilon r calculated to in this range. So all other parameters like epsilon effective, ring radius, width of ring, length of feed line, outer radius of the ring, inner radius, coupling gap, all these are calculated. So for a beginner who are starting this just for the first time, so I have a standard dimension of, we take it as a rectangular piece. So there are some standard steps on HFS software. So just once we open the software, I have to make a ground, like you can see the interface, then making the substrate on that, then making the outer ring as you can see over here. Then we have to add the feed lines like you can see over here. Then assign the lump port to the sensor with 50 ohm impedance. This is of course with the in the software toolbox itself I am doing. Then assigning the environment as a radiation box for the sensor as shown in figure 6.9. So I have to fix into the this particular zone. Then validating the design to check if there is any overlapping of the design part. Then after validation we go for setting of the resonant frequency for the sensor in the ISM band. And then we got a signal like S21 that is shown over here. Basically what is S21? S21 is there are two ports. I am sending signal from one and getting output at the two. So sensing from two and releasing it from the one port. So that is the way we see what is the frequency value and what is the loss over here. Like it should be less than -10, as like in this case I am getting. So this is considered to be the acceptable one. So this is the interface that we see on our setup, typical VNA setup that is available in our lab. Once we calculate the things in a software, then we make actually the ring resonator using a 3D printing. Like for the substrate part, the dielectric part, we can make using a polymer printer and then attach the conducting part, right? That conducting part can be easily prepared on a metal printer. Then doing the assembly VNA setup, that is called vector network analyzer, that is actually being used for getting the different type of the peaks. And I am getting the output where I am getting the first peak. As you can see in this case, I am getting it at around 2.75, followed by the second peak at 5.2 gigahertz with a loss of -35 and -32, which is highly acceptable as regard to the functioning of this type of sensors are concerned. Then there are again set of equation for the design of microstrip patch antenna, which are given for calculating the electric constant at a particular frequency. So using these set of equation, basically we can calculate all the dimensions of the microstrip patch antenna. In the first stage, we only developed a ring resonator, which was used for the contour verification of the electric constant. So once it is done, the next stage is the developing of the sensor, that is the microstrip patch antenna, and using the set of equation given like from 11 to 16 over here, we can design a microstrip patch antenna. Here is the one example is given in which all the dimensions were calculated based upon the calculated electric constant value, right? And then for making a MPA, that is called microstrip patch antenna, in the HFS software, again opening the software, making the ground, then putting the substrate, then you can see over here making the patch over the substrate, then assigning a again the lump port to the sensor with 50 ohm impedance, then assigning the environment in the radiation box, then validating the design. Like in the previous case for the ring resonator, we have seen for the overlapping of the design part, and after validation setting up the resonant frequency for the sensor to resonate in the ISM band, setting the frequency sweep as you can see over here. So I am getting here the S11 signal. Now from the same port I am releasing, and I am again trying to see what is the signal received at that particular location. So S11 parameters we are measuring over here. So after the simulation result, these are again validated using a VNA, and we try to correlate what is the output in the HFS software and what is the output through the VNA. So this is one of the common practice to see whether the simulation part is almost equivalent or near to the fabricated part using the VNA observations. Then after we are able to make a sensor, followed by procedure of ring resonator, then microstrip patch antenna. The next important thing is to calculate the specific absorption ratio. Again, this is calculated using a HFSS software. Actually, there is a standard protocol like in our country. The value of SAR should be less than 2 for safe human use. Like in this particular case, as per the International Commission on Non-Ionizing Radiation Protection Guideline, this SAR value should not exceed 1.6 watt per kg. So, for that purpose, what we assign is the muscle, fat, and skin tissues. Their basically permittivity values we assign, and we try to see this SAR value whether this is a within a acceptable limit or not. So similarly, we can assign these values for depending upon the actual environmental condition. Like suppose you want to make this sensor for some sensing the frequency signal in case of the animal. So we'll talk about the fat tissues, their permittivity values depending upon that particular, let us say if it is a case of cattle, then taking the values for that. Similarly, in case of human, these datas are available for the from the standard data handbook, right? Now we see how this is helpful in getting a IoT based solution, and specifically for the digital twinning. Like we have seen in our some of our previous examples, like we are interested in developing a digital twin which can be used for real time monitoring of that type of patient, that we will see typically in the form of 2 3 case studies that I will present in my coming session. But one takeaway till now is I have developed a sensor, I have calculated some of the fundamental requirements of the dimension part, then only I will fabricate. So once I will fabricate using polymer printing or gel printing or metal printing, then I will assemble, and then I will attach with a low voltage source, and will get the output in the form of change in the dielectric property. And finally, the this change we will use for sensing the or the real time monitoring of that particular activity, patient, or any end user application. So that we will continue in our coming session. I hope the basic information is helpful, and thanks for watching. Thank you very much.